Hello guys, welcome back again. Last video, um, we talk about why do we use numerical methods, and the short answer is it's because not all equations are solvable analytically, and so we need to have another way so as to find the solution uh, without doing the hard analytical part. Now, let's have what is numerical methods? Okay, what is numerical methods? Then what's numerical methods and analysis? So, numerical methods is actually, okay, I'll write it here. Numerical methods are just set of procedures so it's step 1, step 2, step 3, like that, used to approximate a solution okay, and we do it iteratively. That is, we do the procedure, the set of procedures iteratively until our solution is within the specified degree of accuracy. So it's iterative in nature. So that's a numerical method. And another thing, numerical methods uses the simple mathematical operations, because that's what our computer uses. Let's just so numerical methods only uses simple mathematical operations which our computer can do. Okay. Now what's on the analysis part? In the analysis part, here we have how do we model the system? What method are we going to use? When should we stop? When should we stop? Yes. How do we interpret the result? So things like these. Well, this is what our class would be. Now, in order to let's have this one. Let's have this term, mathematical model. In numerical methods, we will be working upon a mathematical model. So what is a mathematical model? A mathematical model is just an equation describing your process or system. In mathematical terms. And a mathematical model is of this form. The dependent variable is a function of your independent variable your parameters and your forcing functions. Dependent variables. So this is the entity that varies according to this, or depends according to this, and this is what we want to find out. Independent variable, so it does not vary according to other factors. This is usually the dimensions along which we determine our dependent variable. Parameters. Parameters are system properties, let's say the mass of your system. Okay. Forcing functions. Forcing functions are outward forces that acts upon our system. So basically a mathematical model is like this, and in numerical methods and analysis we'll be dealing with that. We will be applying the method to here, to this model. Let's have an example for clarity. Let's say, okay. Okay, let's have this example to illustrate what numerical methods is. But first, let's solve this analytically, then solve this numerically in order to compare and contrast and appreciate numerical methods. Let's transfer the problem here so as to have more space. So in this problem, we have the mass of the parachutist, then we also have the drag coefficient, and we are to determine its terminal velocity. Okay, so first, what's the term terminal velocity? We know that when a person or when an object is in free fall, his velocity increases until such time that the net force acting on the system is zero, such that his acceleration becomes zero. Or in other words, his velocity increases until such time that it reaches the velocity at which it won't increase anymore, or it reaches a constant velocity. So that constant velocity, the upper boundary of that velocity, of your velocity, of the velocity of the free-falling object, that's what we call the terminal velocity. Therefore, to find the terminal velocity, we need first to come up with an expression of our velocity. Okay, so for that, we can use the second law of motion. That is, maybe I'll write it here. The net force acting on a system is equal to the mass times its mass times acceleration. Now, in this diagram, there are two forces acting on this object while this is falling or moving downward. That would be Fg, that is the force due to gravity, and the Fr, that is force due to a resistance, or we can also say drag force. Now, I took this, the downward direction as positive, okay, but you can also take the upward direction as positive. You just have to be consistent with the sign, okay, but this time I'll just use the downward direction as positive. Take it as positive. Now, force due to gravity is equal to mass times gravity. Drag force is equal to the drag coefficient times the velocity of your object. Now, there can be many forms. For example, the squared, the v squared. There can be many forms for the drag force. However, I just take this one for its simplicity. So let's divide this with its mass. Then let's interchange. So that would be okay. And we know that acceleration is just the derivative of your velocity with respect to time. So, as we can observe from our Math 16 differential equations, this is a variable separable differential equation. So we can rewrite this as then let's integrate. Now, for this, for the left side, we let u be equal to g minus c over mv. Let's take the derivative of ru with respect to v. That is so this is now equal to negative c over m. That is dv is equal to negative m over c du. Let's substitute this one with this one. That will become now okay. This is equal to plus our integration constant. Then we use E. We'll have the absolute value of u is equal to t where k is equal to k1. Okay. And u is now we know that the velocity is increasing. No, that the velocity, yes, the velocity increases until it reaches a constant value. Therefore, our velocity prior to opening the chute is not negative. Therefore, we can just take out this one, the absolute value. Because our velocity, in this case, as he jumps and reaches a constant velocity, it won't be negative. Now let's rearrange terms. So we'll have transfer, so that would be g. Okay. No, it's minus. Okay. Now, let's find the value of our k, our constant. We can use, since we know that at time equal to 0, that is the moment he jumps, he has 0 velocity first initially, so that would be this is 1, so it'll be taken away. Therefore, it's 1 taken away. Therefore, our k will be equal to g. Then we will have this okay, so this will be now our expression for our velocity. Let's substitute the values. So we'll have mass of 68.1, 12.5, C. This will be equal to Okay, so we have now come up with the exact solution to our velocity at any time t. Maybe to illustrate this, let's take a table of values. Let's have this one as our time. No, maybe here. Time in seconds and our velocity in meter per second. 0, 2. At time, if we are to substitute these values here, we will have our corresponding values of our v, and that would be 16. So as you can see, or as you can observe in these values, at first the parachutist accelerates at a much faster rate, and eventually acceleration reaches 0, which in turn results in a velocity which is constant. So that's why it reaches this terminal velocity of 53.39. And maybe you can also see that this one is actually this one. And that is, as time goes to infinity, this one, this, since it's negative, so it will, since it's negative, it will become 0. So that's why it's, the terminal velocity will become 53.39. Now I plotted that on this graph. At 2, it's 16. At 4, it's 27. Okay, so if we are to graph this one, it will become like this. Until it reaches the terminal velocity of 53.39. But that would be before he opens his chute, because as he opens his chute, your velocity will then decrease. Then let's have, okay, so this is the analytical method of solving this problem. That is, we need first to come up with an expression for our v. So this time we've got the exact solution for our velocity.